Finding a transitive closure of a relation is not an easy exercise. For example, this relation defined over a set of 1, 2, 3, 4 contains these 4 ordered pairs. Now we need to include these 4 ordered pairs into the relation for it to be transitive. But simply adding these 4 ordered pairs into the relation may not be sufficient to make it transitive. This is because when we add, for example, an ordered pair 3, 1 into the relation, the already present ordered pair 1, 3 into the relation makes it necessary for us to also include ordered pair 1, 1 into the relation for it to be truly transitive. It is because of this that the finding transitive closure of a relation becomes a bit tedious procedure. Now, before we look into the procedure of finding transitive closure of a relation into detail, we need to understand one concept, that is a concept of path in a diagraph. A path from A to B in a directed graph G is a sequence of edges given by x0, x1, x1, x2, and so on, xn minus 1, xn, where initial node x0 is equal to A and terminal node xn is equal to B. Now, two vertices A and B in a directed graph representing relation R are connected by a path of length n, where n is a positive integer if and only if the nth power of R contains ordered pair AB. Now, finding the transitive closure of a relation is equivalent to determining whether the pairs of vertices are connected by a path in the graphical representation of relation R. Now, before we look into the Roy-Warwell algorithm for finding the transitive closure of a relation, let's see what a connectivity relation of a given relation is. The connectivity relation of a given relation consists of the ordered pairs AB such that there is a path of at least length 1 from A to B in relation R. Now we know that the nth power of R consists of ordered pairs AB such that there is a path of length n from A to B in relation R. On this basis, we can say that the connectivity relation of R is simply union of nth power of R, where n ranges from 1 to infinity. And practically the range of n is from 1 to k minus 1, where k is the number of elements in the set on which the relation is defined. If R is a reflexive relation, then the connectivity relation of R is also reflexive. This is because R itself contains all the ordered pairs of nature AA for all the elements of set A on which the relation is defined. Now, the connectivity relation is simply union of all the nth power of R. It is bound reflexive because the union contains relation R itself. On the similar line, we can also argue that if R is a symmetric relation, then the connectivity relation R is also a symmetric relation. However, if R is irreflexive relation, R2 may not be irreflexive, and therefore the connectivity relation of R may not be irreflexive. The matrix representing the connectivity relation of R can be obtained by simply performing OR operation on the matrices representing all the powers of R. For example, MR represents relation R. Then MR2 can be obtained by performing bitwise product on MR. Similarly, MR3 can be obtained by performing bitwise product between MR and MR2. We repeat this procedure until we find the matrix representation of MRn minus 1 and MRn to be the same. The matrix representation of the connectivity relation R can be simply obtained by performing OR operation on all the matrices representing the power of relation R.
Now let's see how the Roy-Warwell algorithm finds the transitive closure of a relation R. Let's say relation R is defined over the set of A with n elements. MR is the matrix representation of relation R and MR asterisk is the matrix representing the connectivity relation of R. Let's also assume that V1, V2 and so on Vn is the arbitrary listing of the elements of set A. The elements of set A are also the vertices of the graph representing relation R. So basically, Warwell's algorithm constructs series of 0-1 matrices to find the matrix representation of the transitive closure of relation R. These matrices are denoted by W0, W1 and so on Wn, where W0 is nothing but the matrix representation of relation R itself, and Wn represents the transitive closure of relation R. Wn is constructed on the basis of W0 by constructing series of intermediate matrices denoted by W1, W2 and so on up to Wn minus 1.
Here is that example of finding the transitive closure of a relation by employing the Roy-Warwell algorithm. The relation R represented by this graph here is defined over the set of ABCD. Now, in order to find the transitive closure of this relation, we have to construct the series of 0, 1 matrices represented by W0, W1 and so on up to W4. We go up to W4 because there are 4 vertices in this graph. We would have gone up to W5 had there been 5 vertices in the graph. Let's also assume that this is the arbitrary sequencing of the vertices of the graph, where V1 is equal to A, V2 is equal to B, V3 is equal to C, and V4 is equal to D. In this series of 0, 1 matrices, W0 is the matrix representation of the relation itself, and W4 represents the transitive closure of the relation. We construct the intermediate matrices W1, W2 and W3 on the basis of W0 to eventually find the matrix representation of the transitive closure given by W4 here. So as I said, W0 is the matrix representation of the relation R itself. So here is W0, which is equal to MR. Now when we are constructing W1, we have to represent an element belonging to the ith row and jth column by 1. Whenever in this graph the ith node and jth node are connected by a path such that the internal vertices of that path belongs to the set of A only. Here we are considering A, or rather the first element of this arbitrary sequencing of the vertices, because we are dealing with W1. Also, it is important to note that all the ordered pairs in this graph which are connected by the path of length 1 are also represented by 1 at their corresponding places in W1. This is because they do not have any internal vertices, and therefore they fulfill this condition of if having a path, the internal vertices must be belonging to the set of A. Now, in addition to those ordered pairs which are connected by the path of length 1, we also need to take care of those ordered pairs which are connected by the path of length more than 1 but are having the internal vertex of A. Now there are 2 such ordered pairs in this relation. One is CD connected by the path C to A to D, and another is BD connected by the path B to A to D. Now because there is a direct edge from C to D, this ordered pair CD is already represented by 1 at its corresponding place in W1. We also need to ensure that the ordered pair BD is represented by 1 in the W1 because it is connected by the path having internal vertex A. So this way we obtain W1. In similar way, let's now construct the next intermediate matrix W2. In W2, an element belonging to the ith row and jth column is represented by 1 whenever there is a path in this graph from the ith node to jth node, such that the internal vertices of that path belongs to the set of AB. We have taken the first 2 elements of the arbitrary listing of the vertices because we are dealing with W2. Now all those ordered pairs which are represented by 1 in the W1 are also represented by 1 in W2. This is because either those ordered pairs are connected by the path of length 1 having no internal vertex, or they are connected by the path having internal vertex A. And all those paths are the subset of the paths having internal vertices in the set of AB. So in addition to those ordered pairs which are being taken care of W1, we also need to take care of those ordered pairs which are connected by the paths having internal vertices AB or only B. So in this particular example, we are not having any such ordered pair, and therefore W1 and W2 are the same, but this may not always be the case. In next 0, 1 intermediate matrix W3, all those ordered pairs which are connected by the path having internal vertices in the set of ABC are represented by 1. So for the same reason explained before, all those ordered pairs which are represented by 1 in W2 are also represented by 1 in W3. In addition to those ordered pairs, we have to also take care of those ordered pairs which are connected by the path having internal vertices ABC simultaneously, or B and C together, or just B and C individually. So there are two such ordered pairs, ordered pair DA connected by the path D to C to A, and ordered pair DD connected by the path D to C to A to D. These ordered pairs have not been taken care in W2, and we have to represent them by 1 in W3. In similar way, we now derive W4, which is the matrix representation of the transitive closure of relation R. In W4, all those ordered pairs which are connected by the path having internal vertices in the set of A, B, C, D are represented by 1. So in addition to those ordered pairs which are being taken care in W3, we have to include the ordered pair AA connected by path A to D to C to A, and ordered pair AC connected by the path A to D to C in W4. So this way we find the matrix representation of transitive closure of relation R by using Roy-Warwell algorithm. These are few other examples of Roy-Warwell algorithm to find the transitive closure of a given graph.